This is part 3, and I wanted to begin it with reminding what it is that we're doing. When we're drawing this, we're picking a central atom and we're drawing the Lewis structure. We're counting the central atom electron pairs once we've done the structure to get the electron domain geometry. Then you need to distinguish between bonding and non-bonding electrons, and then you look at the polarity to decide whether the molecule is polar or non-polar. So this has the 6 electron domains, and this section also talks about what if there is more than one central atom. So let's begin. AB6, 2 square pyramids share a base. Let me kind of just draw a structure so you have an idea. Here is my XY plane. Here is my Z-axis. As you've seen in the previous section, sometimes there's an atom there, sometimes there's a lone pair of electrons. But we are going to say when it's symmetrical, all the positions are equivalent. And unlike the 5 electron domains, we have no labels here. I know that sounds odd. And what we, as you have seen, 4 electron pairs in a plane, those would be the 4 Bs. I should have used a different number. And then there is above and below the plane, and that is on the Z-axis, all right? So let's begin with some examples. We have SF6. I will let you do all the calculations to get to the Lewis structure. But what I will do is I will draw the Lewis structure with all of its electrons. And again, I think that's an exercise you need to do because you're the one taking the exam, not me. So what we have here are 6 electron domains, and that we would call this octahedral for electron domain geometry. We have 6 bonding, 0 non-bonding. So octahedra would be our molecular geometry. And the molecule is nonpolar. Now, I kind of blasted through that, but I tortured you in parts 1 and part 2. So this is applying the exact same method. Remember, there's facts, there's methods, there's problem solving. Okay. Here's our next molecule, ClF5. I'm just going to draw it. Chlorine, I'm going to put my 4 fluorines in that XY plane. And now I'm going to put that lone pair of electrons along the Z-axis. Why did I do that? It is so that it is the furthest away from everything else. Where do we know that comes from? We do crystal structures. We do crystallography. Here we're just showing how to apply it. So this is 6 electron domains, and so its electron domain geometry is going to be octahedral. We abbreviate that as OH, I-O, and we have 5 bonding, 1 non-bonding. So our molecular geometry, it's going to get the name. Let's see, what is its name going to be for ClF5? I have to kind of think about it for a second. It is going to be square pyramidal. Now, if I'm the teacher and I have to think for a second, I think you might also. As I look at that lone electron pair, there's nothing to cancel it out. So this is going to be a polar molecule. All right, so here we have the lone pair. Nothing cancels out. It makes it polar. What's our next molecule? Our next one is XeF4. And I'm simply going to draw it. I'm going to put my F's in the XY plane. And I'm going to put my 2 lone pairs along that Z-axis. So again, it is 6 electron domains, so its electron domain geometry will be octahedral. But when I look at it, I have 4 bonding, 2 non-bonding, so its molecular geometry is going to get a different name, and it will be called square planar. All right. Now, I'll let you think for a second. What do you think is going to happen with the polarity? I have a dipole moment in this direction with the lone pair. I have one in the other direction. They're going to cancel, and that's going to make this molecule nonpolar. So once again, lone pairs don't give you the correct answer always. You need to know how to work through. And as I look at my abbreviations, that's really what you have to teach yourself to do. It's not really hard, it's just very laborious. What's on this last slide? Well, what if I have molecules with more than one central atom? You don't want to attack these until you've mastered everything that's happening before this. We have 3 different central atoms. There's carbon number 1, there's carbon number 2, and there is oxygen number 3. So you just take it one step at a time. I wrote tetrahedral, but what do I see here? I see 4 bonding, 0 non-bonding, and that's what made it tetrahedral molecular geometry. What about carbon number 2? I see 3 electron domains, 3 bonding, 0 non-bonding. And let's see, what am I going to say more about that? I'm going to say that it is trigonal planar, because that's what we've been teaching. Now, often students make a mistake. When they look at an OH, they forget to draw in those lone pairs. So someone might say 2 electron domains, linear, but it is far from that. That last oxygen has 4 electron domains, 2 are bonding, 2 are non-bonding, and it is a bent structure. Now that's the kind of question you'll also see on your exam. You will see a molecule you've most likely never seen before, but what you want to do is assign around each separately. It is not hard to do. And when you take organic, remember that is a full year course. You will just see how these molecules intertwine. Think about a protein denatured, what happens to it. That's what you're going to learn in your upper level courses. But proteins are made of different atoms held together by covalent bonds. And that's really why you're in this section and taking this course. Thanks.